When we look up at our sun, it seems so constant, so reliable. But the truth is, it's a dynamic, living star. It actually has this surprisingly predictable rhythm, a cycle of activity that grows and fades over years. But the forces that keep that cosmic rhythm in check, well, that's been a huge puzzle for a long time. So let's dive in and explore the mystery of the sun's incredibly stable heartbeat.
Right, so think of the sun's 11-year cycle as a colossal heartbeat. Every decade or so, its entire magnetic field does a complete flip. But here's the big question. What stops that heartbeat from either just fading away or racing completely out of control? What's the sun's natural regulator?
So this 11-year solar cycle is all about the sun's magnetic north and south poles swapping places. Now, the peak of this cycle, what we call the solar maximum, is when things get really active. We see more sunspots, more solar flares, and these huge explosions called coronal mass ejections. All of this can have very real effects here on Earth, from messing with our satellites to creating those beautiful auroras. So you can see why predicting the strength of each cycle is so important.
At the very core of this cycle is this incredible engine of magnetism. Deep down inside the sun, there's a super complex process that's always working, generating the massive magnetic fields that drive literally everything we see on the surface. And scientists have a name for this engine, the solar dynamo. The solar dynamo, in a nutshell, is like a cosmic conversion process. It takes the main north-south magnetic field, what scientists call the poloidal field, and it twists it, coiling it up into a super powerful east-west field, known as the toroidal field. Then that toroidal field gives rise to a new poloidal field, and the whole cycle just starts all over again. Okay, let's break that down into 3 simple steps. First, the sun's rotation grabs those north-south field lines and stretches them around the equator, really amping them up into these strong magnetic bands. Then, loops of this powerful magnetic field burst right through the surface, and that's what creates the sunspots that we can actually see. And finally, as those sunspots fade away, they leave behind a kind of magnetic ghost that builds up at the poles, creating a new north-south field that's the opposite of the old one. Boom! The cycle resets.
But hang on, this brings up a huge question, right? If this process is constantly making magnetic fields stronger, what stops it from just running away with itself? Why doesn't each solar cycle get exponentially stronger and stronger until the whole system just breaks? There has to be some kind of braking system. And it turns out there is. Scientists have found several natural feedback loops that act like brakes on this solar dynamo. And they have a great name for all these mechanisms put together: quenching. So quenching mechanisms are basically the sun's built-in safety features. They're what's called nonlinear, which just means that as the magnetic field gets stronger, these quenching effects kick in even harder, pushing back and keeping the whole cycle in a stable, predictable range. They're the brakes. Now, for years, we've known about 2 main brakes. The first is latitude quenching. This is all about location, location, location. If a sunspot pops up too far from the equator, it's just not very good at helping build the next cycle. The second brake is called tilt quenching. This one is all about the angle. In really strong cycles, sunspot pairs tend to show up with a smaller tilt, which also makes them less effective. But here's the catch. Even when scientists programmed both of these brakes into their big computer models of the sun, the simulations didn't quite line up with what we see in reality. They were close for sure, but not perfect. Something else was going on. A piece of the puzzle was still missing. And this is where the new research comes in, and it's so cool. It focuses on something that we've seen but never really understood, these mysterious converging flows on the sun's surface. They're like invisible currents in a vast solar ocean. They're called surface inflows. And honestly, the best way to picture them is as giant whirlpools or maybe drains on the solar surface that form around the big active sunspot regions. And they pull in all the surrounding material and, most importantly, the magnetic fields that are stuck in that material. And this quote from the research paper really nails the core idea. The scientists figured that these inflows were directly messing with the dynamo engine. By pulling the magnetic fields inward, they stop that magnetic energy from drifting where it needs to go to help build the next cycle. Simply put, these inflows are acting as a powerful third brake.
So the crucial test was obvious, right? What happens when you add this new ingredient to the recipe? So scientists ran their simulations of the solar cycle again, but this time they put all 3 braking mechanisms to the test.
And just look at this result. It is absolutely fascinating. The solid blue line here, that's what a real average solar cycle looks like. Now check out the red dashed line. That's the computer model with all 3 brakes, including these new inflows. I mean, look at it. It tracks the real-world data almost perfectly over 100 years. To put a number on it, the correlation between their new model and the real sun is 0.85. Now, even if you're not a statistics person, let me just tell you, that is an incredibly strong correlation. It means their model is doing a fantastic job of explaining what the sun is actually doing.
So just how powerful is this new break? Well, the research shows that these surface inflows reduce a cycle's power to build the next one by a massive 10 to 25%. That is a huge regulatory effect that we were completely missing before.
And it gets even more interesting than that. These inflows don't just act as a third break, they actually change how the other two breaks interact with each other. This chart shows the exact point when one break, latitude quenching, becomes more important than the other. Without the inflows, that's the black line, the switch happens later. But when you add the inflows, that's the blue line, it happens earlier. This solved another, much more subtle detail that had been puzzling solar physicists for a while.
Okay, so let's just quickly recap the big takeaways here. These surface inflows are a critical third break on the sun's magnetic engine. They weaken each cycle by up to a quarter, they bring our models into 85% agreement with reality, and they help explain the complicated dance between the other two breaks. They are a major, previously missing piece of the whole solar dynamo puzzle.
It's really an incredible discovery. This phenomenon, which was basically hiding in plain sight on the sun's surface, turns out to be one of the key things regulating its entire magnetic heartbeat. And it really leaves you wondering, doesn't it? If these invisible currents can tame an entire star, what other profound cosmic secrets are we looking at every single day, just waiting for us to figure them out?